In an earlier video, I talked about how part of my senior thesis project involves solving the Schrodinger equation for a given potential numerically. And I thought I might take some time to make a video about how exactly I'm going about doing that. The method that I'm using to solve this differential equation is called Nimrod method, and in order to get a feel for it, to see what it's actually doing, I wanted to apply it to a differential equation that I already knew the solution for. The Nimrod method is useful for solving any kind of differential equation that's of this form. We have some function's second derivative plus some function of x times the function you're looking for plus another function of x equal to 0. Now it's relatively easy to see that the Schrodinger equation fits this picture, right? We have, for the Schrodinger equation, psi double prime of x plus some potential times psi minus some energy times psi equal to 0. This is assuming that it's a time-independent Schrodinger equation. We can simplify this a little bit. Okay, so in this case, our g of x here is going to be this. And it shows how robust this method is because in our case for the Schrodinger equation, s of x is just 0. So the case that I was interested in testing first simplifies this even further. So I'm taking the case where s of x is still 0, and I'm taking the case where g of x is just a constant, 1. So this makes the differential equation that I'm testing y prime double prime plus y equals 0. Second derivative of something plus the function we're interested in equals 0. We might as well just solve this differential equation real quick just to show what we're looking for. So the standard method for solving this is called the characteristic equation, and what you do is you guess. You guess that your function is of this form. Y is equal to e to some scaling factor lambda times x. Now, this is a very normal method of solving this kind of differential equation. So the next step to do is to find the second derivative of this and see if it works. So if we take the second derivative of y, we get y prime equals lambda e to the lambda x, and y double prime equals lambda squared e to the lambda x. Well, that's not even in our equation, so we don't have to worry about that. So if we make our substitution, we get that y double prime lambda squared Great. Well, we can factor out the common factor of e to the lambda x. And this is the equation that we're solving for 0. Well, e to the lambda x is never going to be 0, right? E to any number is still going to give back either it's always going to give back a positive number, actually, right? Even if lambda or x is negative, it just gets pretty close to 0. It's never going to be the thing that makes this 0. So we're able to divide this to the other side, and this becomes the equation that we're solving. And this is pretty easy. What we get if we solve this for lambda, we get lambda is equal to plus or minus I. And our guess was just that y was equal to e to the lambda x. Since we got two values of lambda, two eigenvalues for lambda, our solution is actually going to be a superposition of both until we plug in some kind of boundary condition. So this tells us that y is equal to some constant, c1 e to the ix, plus some other constant, c2 e to the minus ix. Using Euler's identity, we can write this in a more meaningful form, where we can say that this is equal to c1 cosine of x plus c2 sine of x. Great. Now, because this is a second-order differential equation, we need two either initial conditions or boundary conditions, whatever you want to call it, in order to find out what these are. So, some self-imposed ones that I'm going to say are that we're going to say that y of 0 equals 0, and y of h equals h. Now h is just going to be some distance from x0 to the next point. And what I mean by that is if you look at this graph here, I'm drawing some point x0, some point that I'm starting with, and some point x1, and the distance between these 2 points is going to be h. Now I'm going to choose an h that's sufficiently small and think that this is a pretty well-behaved function because it's just cosines and sines, and I'm going to say that y at h is just h. Okay? Now this is, and I'll show you why this is a pretty good initial condition. So if we take this initial condition first, or this boundary condition first, we can plug in 0 for x and y and see what one of these coefficients has to be. So if we do 0 is equal to c1 cosine of 0 plus c2 sine of 0, well, sine of 0 is just 0, so that goes away. Then we get 0 is equal to c1 cosine of 0 is 1, so we get that c1 has to equal 0. So that simplifies one term of our solution. This tells us that this is really, so far, y equal to c2 sine of x. Now, the reason I said that this is a good boundary condition for this is about to become apparent. So let's plug this in. Y is h is equal to c2 sine of h. The reason I said this is going to be a good boundary condition is because for small angles, and I said I'm taking h to be sufficiently small, for very small angles, sine of x is approximately x. And you can find this out by just doing a Taylor series centered on x equals 0 for sine of x. So that tells you that since I'm choosing h to be very small, h is equal to c2 times h. The h's cancel and we get 1 is equal to c2. And what this is doing, what this c2 is doing, is it's normalizing my sine function. It's guaranteeing that it has an amplitude of 1. So after going through all that in a very tedious kind of way that we kind of probably could have skipped a lot of this, is we get that y is equal to sine of x. And if we plug this back into the differential equation, we see the second derivative of sine is just minus sine plus sine equals 0. And it checks out. That's good. So this is a differential equation that's very easy to solve, and I was using this as my jumping off point for using Nimrod method. So again, Nimrod method can solve any equation that's of this form. Where y, g, and s are all functions of x. Now because computers don't understand what continuity is, everything has to be discretized when talking about functions. So instead of talking about we're looking for a y of x, what we're really looking for now is a y sub n. Where, and for this I'm saying that y sub n is equal to y evaluated at x sub n, where x sub n is equal to x0 plus nh. And this is getting a little bit abstract, I'll admit, but h, as I showed when we were just graphing before, is just the increment in between the next point that we're choosing. And n is talking about which increment. So back to the example, if instead of having a continuous sine wave, we have a bunch of points that are equally spaced out, and that spacing is h, what we get is that, say that this is x0, and this is x1, and this distance is just h, then our x2 is just going to be x0 plus 2h. That's going to be it, right? Because that's what this next interval is. It's going to be h here again, and that's just 2h. Now the power of Nimrod method comes from the fact that if you know what y sub n is, and you know what y sub n minus 1 is, keep in mind that this is solving a second order differential equation, so these are really just your boundary conditions again, or your initial conditions. It says that the next point, remember because this is discretized, the next point can be given by this equation here. I'm not going to go into the derivation of how to get to this equation, but just know that you can get to it by doing some clever moves on a Taylor series on this differential equation itself. Another cool thing about this equation is that you see that we're evaluating g sub n's and g sub n minus 1s, g sub n plus 1s, all these kinds of things. But these are already functions that we know. These are specified in the problem, so that's just as simple as taking that known function and plugging in your x values, and that's just going to spit out a number. For our case, our g sub n is still just going to be a constant, and our s sub n's are 0, so this equation simplifies even further. When we get rid of all of the unnecessary g sub n and s sub n stuff, this is the equation that corresponds to solving the differential equation that we know should come out to being sine of x. In order to implement this kind of routine into like a computer code, you first have to specify the number of function evaluations you want to do. And then what I normally always do for my h, which again is just the step size, is I always make it 1 over the number of points that I'm using. If you tell the computer code to keep running until it reaches this number of points, what you also end up telling it is that this y sub n minus 1 becomes your new y sub n. And your y sub n just becomes your new y sub n plus 1. So if you iterate this enough times and say you save all of these data points, and then you also save all of the x values associated with it, you can plot this out and see if it looks like something that you might recognize. And that's exactly what I did for this code here. And you can see when we run it, we get a very familiar sine wave. So now that I know that my code works for the simple case where g is equal to 1, I can now introduce some kind of potential and I'll be confident that it's going to give me reliable results. Those are the famous last words though. Thanks for watching this video. The best way to learn something is to try to explain it to someone else, so this is very beneficial for me. If you guys have any questions about the differential equation that I solved or the code or whatever, let me know in the comment section and I'll see you guys there.